sir.
हाँ
Sir, up है.
अनुराग, अच्छा ठीक है.
Yes, sir.
कुराटोवस्की, ठीक है, अब विजिबल है ना? Okay, so let us define this. So let X tau be a topological space. Topological space. And so we define a closure function, okay? So a function from power set of A to power set of A. We define a function. So the closure function, so let us call it CL, okay? Or you may call it bar. So let us call it CL, okay? Closure of, so in my notes you will see this thing I'm telling you what. So define a function which is given by or defined by A goes to closure A, or you may write this is nothing but A bar, okay? A goes to A bar. So in my notes I wrote A goes to A bar, okay? So this is the function and it satisfies the following property. Number one, A is a subset of A bar. See, if you see the definition, it says that the closure is the smallest subset, smallest closed set containing A. So closure contains A. So here is this thing, A is contained in A bar. Second thing, closure of closure is closure of A. So in other words, closure of closure A is nothing but closure. So this is because closure A is closed. So this you have already seen. If a set is closed, see here, if a set is closed, then it is equal to its closure, okay? For a closed set, A bar is same as A. Okay? Third thing, A union B bar is same as A bar union B bar, or you may write closure of A union B is same as closure A union closure B. Okay? Empty bar is empty. Okay? So you know this is again true because empty set is closed. Okay? A is closed if and only if A equal to A bar. So let us prove this. So yeah. Prove this. So this one is clear from the definition of closure. Okay, you know the closure is the smallest closed set containing A. So since it is A bar is containing A, this one is true. Second thing, let us prove the second part. So A bar is clearly contained in A bar, but this is by 1. This is from 1. Okay, from this is true. Okay. Now, since A bar is the smallest closed set, okay, see here, smallest closed set containing A. So now use above observation, which says that a set A is closed if and only if, okay, yeah, we will, okay. So before proving this, let us prove this fifth part that you already know. This part you have proven last time. Okay, so here you have proven it. at this place. If A is closed, then A equal to A bar. And this is very easy. So if A equal to A bar, since A bar is closed, A is closed. Okay? So this shows that A is closed. Second part, when A is closed set, is a closed set, then by definition A is contained in A, and A is the and A bar is the smallest set, is the smallest set containing A. Okay? So this means what you get is from here, since from this and from this you will get A bar is contained in A. And you already know that A is contained in A bar, this implies A equal. Okay? So fifth part is done. So if fifth is done, then fourth is automatically done because empty set is closed. And then clearly second is also done from using this. Okay, the only thing that remains to prove is the third part. That is, closure of A union B is closure of A union closure of B. Okay, this is also very easy. So third is A union B bar is A bar union B bar. Okay, so it's very easy. A is contained in A union B, you know, and B is contained in. This is very easy. So this shows that A bar is contained in A union B bar, and B bar is contained in A union B bar. Okay. From here, what you get is A bar union B bar is contained in A union B bar. Okay. So now you have to prove other equality, other inclusion. Okay. So now what you have is, you know, A is contained in A bar and B is contained in B bar. This implies A union B is contained in A bar union B bar. Okay, is this correct? So now take bar both sides. This means A union B bar is contained in A bar union B bar whole bar. But being A bar and B bar being closed sets, their if you take their union will be closed. Okay, right here, since A bar and B bar are closed sets and they are finite. Okay, being okay, therefore A bar union B bar being a finite union of closed sets is closed. Okay, so this implies, since A bar union B bar is closed, you know, if we take its closure, we will get the same set. Okay, so from this, what you get is A is contained in A bar union B bar. Okay, now what you have already shown at this place, A union B is contained in A bar union B bar, and hence at this place you have shown that A bar union B bar is contained in A union B bar. Now you have shown that A union B whole bar is contained in A bar. So this implies A union B bar is equal to A bar. So this is done. Okay. Now we will define a topology on X using these closure axioms. Before that, let us see whether this last equality, whether this third equality that we just proven, okay, whether this is true in case of intersection or not. So whether this is true in case of intersection, okay. So when so is it true? So A intersection B equal to A intersection B bar, whether this is true or not, okay. Can anyone tell me, can anyone guess what it should be? Is it equal or is it not equal? हेलो
सर इक्वल होगा
इक्वल होगा
सर, होगा क्योंकि जो ऊपर वाला यूनियन वाला ऊपर है तो इंटरसेक्शन वाला भी ऊपर इक्वल होना चाहिए।
नहीं, होना चाहिए और होगा में बहुत अंतर है ना। ऐसा होना चाहिए, हमारे देश में गरीबी नहीं होनी चाहिए, लेकिन है, क्या करें। तो होना चाहिए या नहीं होना चाहिए वाली बात नहीं, होगा या नहीं होगा। ओके, देखते हैं हम। टेक एक्स इक्वल टू आर विद यूजुअल टोपोलॉजी, ओके। विद, आपको ये ध्यान देखना, टोपोलॉजी कौन सी वो हमेशा याद रखना है, ठीक है। विद यूजुअल टोपोलॉजी। सो आर के ऊपर आपने बहुत सारी टोपोलॉजी देख ली, इनडिस्क्रीट टोपोलॉजी, डिस्क्रीट टोपोलॉजी, यूजुअल टोपोलॉजी, कोफाइनाइट टोपोलॉजी, को काउंटेबल टोपोलॉजी, लोअर लिमिट टोपोलॉजी, अपर लिमिट टोपोलॉजी, और भी बहुत सारी टोपोलॉजी आप देख चुके हैं, ठीक है। ये आप देख चुके कहां पर, आर में। तो आप ध्यान देना कहां पर हम बात कर रहे हैं। नाउ टेक ए इक्वल टू 0,1 ओपन इंटरवल, b इक्वल टू 1,2 ओपन इंटरवल, ओके। So what is A intersection B? What is A intersection B? Hello?
1।
किसने बोला ये? कोई दूसरा, कोई और बोलना चाहेगा? What is A intersection B?
सर इंटरवल ना करके वो तो एक पॉइंट आ रहा है
सर। बी क्या है यहाँ पे, 1 2 है।
फिर से लिख रहा हूं, A इक्वल टू ओपन इंटरवल 0,1, B इज ओपन इंटरवल 1,2, व्हाट इज देयर इंटरसेक्शन?
सर 5 होगा।
कौन बोला ये?
सर नेहा बोल।
हाँ, नेहा ने ठीक बोला, ये एम्प्टी सेट होगा, ठीक है। क्योंकि 1 तो दोनों में सेट में नहीं है ना, 1 ए में भी नहीं है, बी में भी नहीं है। लेकिन अब आपसे पूछना चाहता हूं कि एक क्लोजर क्या होगा? व्हाट इज ए क्लोजर एंड व्हाट इज बी क्लोजर? ए क्लोजर इज व्हाट इज द स्मॉलेस्ट सेट कंटेनिंग ए। आप सारे क्लोज सेट लीजिए, ए को कंटेन करने वाले, उनका इंटरसेक्शन ले लीजिए, क्या मिलेगा आपको? Smallest set containing A is smallest closed set containing A is closed interval 0,1, okay? अगर किसी को इसमें दिक्कत है तो वो एक बार फिर से सोचिए ये क्यों हो रहा है, क्या? ये सब आप बीएससी में पढ़ चुके हैं, इसीलिए मैं ये डायरेक्ट लिख रहा हूँ। एंड क्लोजर ऑफ बी इज 1,2। नाउ व्हाट इज ए इंटरसेक्शन, sorry, A bar intersection B bar? What is this? Yeah?
यस सर।
हाँ, बताइए क्या है? आपकी आवाज कट रही है, थोड़ा आराम से। 1 होगा ना? ओके, ये आपने सही बताया। बाकी एक चीज यहाँ देखिए, क्योंकि एम्प्टी सेट का क्लोजर एम्प्टी सेट है, बिकॉज ऑफ दिस फोर्थ प्रॉपर्टी, एंड क्लोजर ऑफ एम्प्टी सेट इज एम्प्टी। दिस मीन्स यहां पर अगर हम इसका क्लोजर लें तो एम्प्टी सेट का क्लोजर आता है, और ये क्या आता है, एम्प्टी सेट आता है। यू सी दिस सेट A intersection B closure, and second set intersection of closure of A and closure of B, they are not equal because empty set is not equal to 1. However, what is true is this: A intersection B closure is contained in A closure intersection B. Okay? In this case, this is true. But this equality is not true. Okay, in general, this is not true. General, we have this. Now, what we do, we define topology in terms of Kuratowski closure. Okay, define topology in terms of Kuratowski closure. So here is a theorem. It's very easy theorem. You will, I think, you will do it yourself. So what we have is, we have a set X, let X be a set, okay, and now we define chi, okay. So chi is the same function which we defined above. We call it A bar here. A goes to A bar. So we now define it as chi. Okay, satisfies the following. Number one, A is contained in chi A, means closure A. You can replace it by closure, okay. Let me call it closure. अच्छा, chi से काम करते क्योंकि आप फिर let me call it closure, क्योंकि अभी हमने ऊपर closure ही नाम दिया है इसका. So call it closure. A contained in closure A. Second, closure of closure A is closure A. Okay, ये हम प्रूव कर चुके हैं. Closure of A union B is same as closure of A union closure of B. Okay, fourth thing is closure of empty set is empty set. Okay. Now, fifth one is, if A is closed, then closure of A is A. Okay. Now, what we do, we define a set. Okay, let F, funny F, this is F, is all subset of X such that A equal to closure A. So what we are doing here, we are taking collection of all closed sets. See, A is closed, depend only closure A is A. So we are taking all closed sets, okay, and define tau. Tau is all those subsets G of X such that X minus G is closed. Okay. Wait a minute. Okay, so here we are taking all subsets of X such that their complement is closed. Okay, you see this? So this means this is nothing but it says closure of X minus G is X minus G. Okay, by using the definition of F. Then the conclusion is then tau is a topology on X, and for every A subset of X, A bar is the closure A. Okay. So A bar means whatever we, so this A bar represents closure. Okay. So you may see why I was taking chi here, because I fixed this notion for closure, but okay, it is okay. So this closure A is closure of A. You know this by definition is the smallest closed set containing A. So let us proof is very easy. Proof is very easy. Okay. Let's see a proof. So by definition, see from here, closure of phi is phi. So phi equal to closure phi. This means phi belongs to F. Phi belongs to F. Okay, clearly phi belongs to F. And second thing is X by definition is, see, this is from here. Replace A by X. X is contained in closure of X, but everything is subset of X itself. Okay. So from here, what you get is X is equal to closure of X. So this means X belongs to F. Okay. Empty set and X both belong to F. Now see the definition of tau. From tau, you see all those subsets whose complements belongs to F are elements of tau. So clearly this implies X minus empty set is X, okay, which belongs to F. This implies empty set belongs to tau. Second thing, X minus X is empty set which belongs to F. This implies X belongs to tau. Okay. So first axiom of topology is satisfied. Now second is for what you will see for unions. Okay, for arbitrary unions. Okay, is this correct? Let's do that. Now first what we do, we first claim that if A is a subset of B, then closure of A is subset of closure of B. Okay, first prove this. So how will we do this? A is subset of B. Okay, then you know this B can be written in this case, this B. So you have this is A, this is B. Okay, and this part is B, this part is B, and this part, oh sorry, this part is B minus A. Okay, this part is B minus A. So A is nothing but sorry. It is A, it is B. Okay, A is subset of B. So then you will write B as A union B minus A. Okay, and A and B minus A, they are disjoint. Okay, they are disjoint. So from here, what is closure of B? Closure of B by this closure of A union B is closure A, closure B. So from here, what you get is closure B is same as closure A union closure B minus A. Okay, is this correct? So this closure B is union of these two. This implies closure of A is contained in closure of B. Okay, this is the easy part. Now, what you do, you take an arbitrary collection of sets inside tau. Okay, so if you have the gi, then by definition of tau, x minus gi belongs to f. Okay, this means x minus gi is contained in f. Okay, call them ei. Ei equal to x minus gi. In call them ei. Okay. Now note that for every j in here, intersection of all ei's is contained in ej. Okay, and from above, now you take closure of this. This is closure of ej. Okay. Is this correct? Is this correct or not? And you see, this left hand side expression is independent of j. Okay. Kuldeep, someone says, Kuldeep, is there any problem? कुलदीप कुमार, हाँ कुलदीप बताइए क्या दिक्कत है?
नो प्रॉब्लम।
हेलो, तो आपने ये अपना हाथ उठाया है, इसका मीनिंग क्या है? गलती से हो गया वो?
यस सर, गलती से हो गया।
Okay, so we have, so far we have this thing, and this part is independent of j, and what you do, you take intersection over all j. Okay, so from here you will get intersection I in I is contained in intersection j in this closure of ej. Okay, but closure of ej for this ej, for you see the definition of f. So ej belongs to f, and for all elements in f, a is same as closure of it. Okay, so since these ej's they come from f, so this means this is same as ej. Okay, is this correct? And this contained in closure of, this is by the definition of, this is first property. Okay, this comes from first property. So what you observe is See this inclusion, we started from this and we are ending at the same thing. So this means everything is equal, okay? So it is kind of sandwich theorem. So A contained in B contained in A implies A equal to B. It is like this. So what we get is implies closure of intersection EI is same as intersection EI. Okay? Do you see this? Is this correct? Once you get this equality, this means this intersection is in this funny F. Okay? Since this intersection is in funny F, this means its complement is in tau. So x minus I EI is in tau. Now use De Morgan's law. So De Morgan's law says that this is nothing but union of x minus EI, I in tau. Okay? X minus EI is nothing but GI. So you are done. Okay? You are done. Now what you do, you replace arbitrary thing by a finite collection. Okay? Now take G1, G2, Gn in tau and assume that x minus GI is GI. You have to show that there is in tau. So, but you know x minus GI, these are in F. And you know finite union of closed set is closed. Okay? So this means EI, I1 to N, this belongs to F. This is same as saying x minus UI equal to 1 to N, EI is in tau. But this is nothing but intersection I equal to 1 to N, x minus EI, tau. And x minus EI is nothing but this is nothing but GI. So you are done. Okay? You are done. So what you have proven is tau is a topology. Now you have to show that this function CL is nothing but the closure of it. Okay? This is nothing but closure of it. So what you do, you first take a subset A. Okay? By second property, what you have closure of A is closure A. Okay? So this means this closure A belongs to F. Okay? Now what you take an element in F such that A is subset of B. Okay? Then by same, we have already shown this. If we have two sets A and B, where A is the subset of B, then closure of A is contained in closure of B. And since B belongs to F, closure of B equal to B. This means closure, so this closure A is the smallest element of F that contains A. Okay? But this is the definition of A bar, that is the closure. Okay? So this means closure A is A bar by the definition of closure. Okay? So this is how we define topology using Kuratowski closure axioms. So we have seen closure thing. Now we see neighborhood system. Okay, neighborhood system means using interior. We have already seen this. So let us see definition of neighborhood and do the same thing. As you did for closure, we will do this for neighborhood. Okay. First, we recall the definition of neighborhood of a point. Neighborhood of a point. So let us see the definition. Let X tau be a topological space and X be a member of capital X, a subset N of X is said to be a tau neighborhood. I will write NBD, okay? For neighborhood, I will use this notation NBD of X if there exists a tau open set, okay? G, tau open set means G is in tau, such that X is in G and G is a subset of N. Okay. This means a neighborhood of a point is any set which contains an open set containing that point. Right? So from here, what we see, open sets are neighborhood of each of its points. So open sets are neighborhood of each of its points. So because G is subset of itself, okay, and so from here, from this definition, okay, from here, what you observe that open sets are neighborhoods of each of its points. Okay. Now let us see some examples. Okay, let's see some examples. Let we take a discrete space, XD be a discrete space, and X in X. Okay. In this case, each singleton, okay, each singleton is a neighborhood of itself. Okay. Why? Because you know this subset X, which is a singleton set, belongs to D. So call it N. Okay. So this means X belongs to here and it is contained in N because it is equal to this. So this means this singleton is itself, because this is open, this is neighborhood of X. And any set, any subset of X which contains this point X is a neighborhood of it. Okay? Any subset of X which contains X is a neighborhood of this point. Okay? This is the case for discrete topology. What about indiscrete topology? So, in discrete topology, can you tell me what are all neighborhoods of a point in discrete topology? Hello? Neha?
Yes,
Hello,
sir.
Neha?
Yes, sir.
हाँ, indiscrete topology में neighborhood बताइए कौन कौन से होंगे? अच्छा, indiscrete topology में open sets कौन से होते हैं?
सर आर एलिमेंट्स ऑफ एक्स मतलब सर उसमें सारे एक्स के एलिमेंट आ जाते हैं जो ओपन सेट में होते हैं.
नहीं, मैं पूछ रहा हूँ, आप मेरा क्वेश्चन समझी? मैंने इंडिस्क्रीट टोपोलॉजी बोला, मैंने बोला इंडिस्क्रीट टोपोलॉजी में ओपन सेट्स क्या होते हैं?
सर ये सर आर ओपन सबसेट ऑफ एक्स.
वो तो डिस्क्रीट टोपोलॉजी है ना, ऑल सबसेट्स आर ओपन इन डिस्क्रीट टोपोलॉजी. इंडिस्क्रीट ट्रिवियल टोपोलॉजी
सर फाइव और एक्स होते हैं.
फाई और एक्स होते हैं ना.
Yes,
टाउ
Yes,
दिस
sir.
आई इज नथिंग बट फाई एंड सो ओपन. यहाँ पर नेबरहुड क्या होगा फिर? So in this case, X is the only neighborhood. X is the
Yes,
only
yes,
neighborhood.
sir.
Okay?
Yes, sir.
Each of its points. Okay? Now, here is another example. Take X equal to 1, 2, 3, 4, 5. And tau is, take empty set, take X 1, 1, 2, 1, 2, 3, 1, 2, 3, 4. Okay? So find all neighborhoods of 1. Find all neighborhoods of the point 1. तो कौन से neighborhood होंगे 1 के? So 1 को कंटेन करने वाला ओपन सेट कौन?
और सभी हैं।
हाँ, 5 के अलावा और सारे हैं। जो भी ओपन सेट 1 को कंटेन करने वाला है वो एक नेबरहुड होगा। ठीक है? एनी डाउट? हेलो?
नो सर।
ओके। अब एक थ्योरम हम देखते हैं, एक रिजल्ट। Let X tau be a topological space, okay, and A is a subset of X. Then A is open if and only if it contains neighborhood of each of its points. Okay, but we know by definition, it is by definition of open set, you can easily see this. Okay, let us prove first. Suppose A is open. A is an open set. Okay, A be an open set. अभी आपको क्या प्रूव करना है कि ये इसके सारे सेट्स का एक so it contains neighborhood of each of its point. Okay, so since A is open, you know, A can be written as basis elements of tau. Okay, you have a base for tau. A can be written as basis element. Okay, now take an arbitrary element X in A. Okay, an arbitrary element X in A. That element X will belong to some Bx. Okay, where Bx is sum of Bj or some J. Okay, so from here what you get, this X belongs to Bx and it is contained in A. Okay, this Bx is the neighborhood of each of its point because it is open. Okay, so this is one thing, and you may also say like this, by the definition of neighborhood, so what we get, so look at the definition. There exists, so a set is neighborhood of X if there exists an open set G such that X in G and it is contained in A. So in fact, you may see it directly. What you say that X belongs to A and A is contained in A. So this A is open. Okay. So therefore A is neighborhood of each of its point. Okay. Converse part is also true. Conversely, let assume that A contains a neighborhood of each of its point. Okay. Conversely, A contains a neighborhood of each of its points. So this means there exists a neighborhood and A, neighborhood and A for A in A, okay, such that A belongs to NA and it is contained in A. By the definition of neighborhood, there exists an open set SA contained in NA and contained in A. Okay? So what you do, you take set of, so this set of all unions. Okay? So since S is union of open sets, so therefore S is open. S is open because it is union of open sets. Okay? So an arbitrary union of open set is open. So your claim is now prove it S equal to A. Okay? So this is very easy. So suppose X belongs to A, okay? Then this Sx, this is contained in S. Okay? There exists some Sx which is contained in S. So this implies A is a subset of S. Now what you have to show that S is contained in A. S is contained in A. Take Y belongs to S. Okay? So this Y will be some SA. Y is in some SA. Okay? And this SA is contained in A. So this means Y belongs to A. And you are done. Okay? Let us see some properties of neighborhood. These are very easy properties. You all know the properties of neighborhood and you can prove them. So I leave this for you. Every point of a topological space X is contained in at least one neighborhood. Okay? So this is true because X is itself an open set. Therefore, any point is contained in X. Okay? So first one is true. Second, intersection of any two neighborhoods of a point is a neighborhood of that point. But this is again true because you know intersection of two open set is open. Okay, you have to use that. Third thing, any set which contains a neighborhood of a point itself a neighborhood of that point. Okay, and this is by definition true. Last thing, if n is a neighborhood of a point X, then there exists a neighborhood n star of X such that n is a neighborhood of each of points of n star. Okay, so I leave this the proof of these properties for you. At the end, I'll show you, we will define a topology on X using this neighborhood system. Okay, so this is also easy as the topology coming from closure axioms. Okay, so you will do it your own. Let there be associated with each point x of a set X a collection, an X star of subsets called neighborhoods. What we do here, we have taken a point x, small x in capital X, and we define an X star is the collection of all neighborhood of X. Okay. So when we call this neighborhood, this means this set satisfies the above property, these four properties. Okay, they satisfy these four properties. Correct? So whenever I say neighborhood, they satisfy. Now let tau be the family of all sets. Okay, all subsets of X. This is the family of all subsets of X which are neighborhood of each of their points. So this means whenever X belongs to G, okay, this implies X belongs, sorry, for each point of G, G is a neighborhood of that point. Okay, then tau is a topology. Topology on X. Okay, this is one thing. Second thing, if an X is the collection of all neighborhoods of X defined by the topology tau, then an X star equal to an X. And this is true for all X and X. So I will leave this as an exercise for you. Please do it your own. Any doubt? Hello? If not, then I'll stop sharing my screen and I will end the meeting.